Thanks, everyone. So as described, I'm Rob. Been working on vLLM for the last couple of years at Neural Magic and now at Red Hat. And really, inside of vLLM, we've spent a lot of the last 12 months working on a variety of topics. But one of the most important ones is mixture of experts models. So I'm going to talk about some of the challenges and solutions that we've built over the course of the past year or so to make these models go as fast as possible on top of vLLM. So to get started and motivate some of the challenges and differences in how MOEs run, I just wanted to start with a little bit of a one-on-one on how traditional dense decoder models like Llama 3 are served today in a multi-GPU environment. And this has been a method that we've had in vLLM from the very beginning, something called tensor parallelism. This is the primary way that more standard, dense Llama 3 style models are deployed, where an individual weight matrix is sharded and split between various GPUs. And there's a very interesting mathematical trick where if you have a activation times a weight times another weight, if we shard the first weight in a column parallel way and the second weight in a row parallel way, we can use one single collective communication operation to synchronize the GPUs. So, for instance, in the MLP layer, we'll have the first W13, which would be this orange matrix here, and then the W2, which is the green matrix here. And so, if we have replicated inputs times a column parallel matrix, will give you sharded outputs, and then sharded outputs times a row parallel matrix plus an all reduce synchronizes all of the GPUs. So this is sort of tensor parallelism 101. Column parallel, row parallel, all reduce. And what we can see is that, this is from the Megatron paper, what we can see is that this is exactly the way that standard decoder-only models are laid out in GPU, where for the MLP layer, we'll have the first matrix laid out in column parallel way. Replicated inputs gives you sharded outputs times a row parallel matrix, all reduce, synchronizes all of the GPUs. And then same thing in attention, where we'll have replicated inputs times column parallel QKV. The attention will happen locally within every rank, gives you sharded output times a row parallel matrix, plus an all reduce, synchronizes the GPUs. So this has been the tried and true method that we've used for a very long time in vLLM to shard standard models. In addition to the weight sharding, there's also a need to shard the KV cache. And so for standard models like Llama 3, which use GQA attention, where we'll have, for instance, 8 KV heads and 32 Q heads, there's a very natural pattern, which is that we can put the KV heads for attention head 0 on GPU 1, the KV heads for attention head 8 on GPU 2, and so on and so forth. So it's a very natural way, as long as we have 8 KV heads associated with the model, to just shard the KV cache, putting the KV heads locally for on each rank. And in fact, the Llama 3 architecture was specifically designed for these single node deployments, since they have exactly 8 KV heads. But what we've seen is that modern models, such as Qwen 3 MoE, will use much less KV heads. So Qwen 3 MoE, for instance, only has 4 KV heads. And other models like DeepSeek R1 will use variants of attention, such as MLA, which compresses all of the KV heads into a single latent KV vector. And this single latent KV vector, there's no way to shard this across a variety of ranks. So if you're running DeepSeek R1 with MLA, you have to effectively replicate the KV cache on every single TP rank, which means you have 8 times the amount of, or 1/8 of the theoretical KV cache usage that you could have if you had a normal setup. And so this has been what has been happening over the course of the past couple of years, which is we've seen these very, very, very large sparse mixture of experts models, where it's very challenging to even fit that model within a single node, which breaks the parallelism scheme, which we've seen, which uses tensor parallelism for the Llama-style models. And we've seen models coming out with these compressed KV caches that don't that requires us to replicate data as we increase the number of GPUs. And so for models like DeepSeek R1, Kimi K2, we really want to deploy these in a multi-node environment and enable ourselves to have as much KV cache space as possible. And the standard way that we've deployed Llama 1, Llama 2, Llama 3 standard GPT dense transformers doesn't really work for these multi-node deployments. And that's very much because as we move from a single node to a multi-node environment, we switch from using the really fast NVLinks that go in between the GPUs to the slower InfiniBand networking in the multi-GPU setup. So given the challenges of running a dense decoder model with tensor parallelism in a multi-node setup, I think we see the shortcomings of that. DeepSeek and DeepSeek-style MLP models have a different parallelism scheme that we can use. And in particular, we've spent a lot of the last year working on optimizing a parallelism scheme which just uses data parallel attention and expert parallel MoE. And rather than using these all-reduce kernels, which require us to synchronize all of the GPUs together, we have the opportunity to use sparse collective operations, which can scale better to these multi-node environments. And importantly, because we're doing attention in a data parallel way, rather than sharding the attention layers and sharding the KV cache, we will just route requests to one of n ranks, which allows us to have the full KV cache utilization without having to replicate the MLA MLA KVs across multiple ranks. So this DP attention, EP MoE allows us to have one copy of the EP weights in a multi-node environment and really have a super large KV cache size that can allow the models to scale well to a multi-node environment. So to give a flavor of how a forward pass kind of works in this DP-EP setup, I've laid out like a simple kind of example here. So in this case, we have 4 requests running on DP1 and 4 requests running on DP2. And so this represents the output of attention, where we have this blue matrix, which is the hidden states after attention for request 0. This request will get routed to some expert based on the router. In this case, that's going to get routed to expert 1 and expert 2. Look at this pink request here, so the third one. This request gets routed to expert 2 and expert 4. So the key operation that we need is to do what we call a dispatch operation. This dispatch operation is going to send the request from the DP rank to the proper expert. So as we can see, this first request in the blue here got routed to expert 1, so it's up at the top center with expert 1, and to expert 2. Whereas the pink request gets routed to expert 2 as well as to expert 4. And so this dispatch operation is sparse. As we can see, we only have to send the request to the proper EP rank. And this is what's going to allow the model to scale to multiple nodes, because we're not actually sending that much data in between the ranks. After the dispatch operation, we have the experts. We can run a standard group gem. And then we need to combine, which is to effectively send the request from the expert back to the original DP rank, which is what you can see after we do the expert layer. And so this dispatch combine operation really sits at the core of making the DP attention EP MoE work together efficiently. So that's the overall mental model for how things work. We run attention independently on all the different ranks. After attention, we do this dispatch operation, which sends the token to the proper rank. We do the MLP independently, and then do the dispatch operation back. So that all sounds great, but it's actually very hard to get this right. And so I'm going to talk through 2 key considerations for making the performance of DP-EP work really well. The first thing that we need is a really efficient implementation of this dispatch gem combine. And the second is we need prefill decode disaggregation. And I'm going to talk about both of these methods, how we did them in vLLM. So the first thing I'm going to talk about is the efficient gem dispatch combine. And several months ago, DeepSeek did their open source week, where they released a huge series of both kernels and just insights about how their inference system works in production. And two of the most important days of this were the Deep Gem Day, which is the efficient gem kernel, and the Deep EP Day, which was the day that released the collective communications. And Deep Gem and Deep EP are co-designed to really work together to make the dispatch MoE combined operation as efficient as possible. So I'm going to talk through how they work, because I think they're pretty cool. First of all, Deep Gem and Deep EP come in two variants. We have one variant that's optimized for prefill, and one variant that's optimized for decode. In the prefill case, these are not going to be compatible with CUDA graphs. There's no static buffers. They're designed to be a little bit more dynamic to deal with all the different shapes that you're going to have during a prefill pass. On the decode side, they're really heavily optimized for low latency, and they're compatible with CUDA graphs. And I think, in particular, the Deep Gem, Deep EP low latency case for decode was one of the most brilliant releases of 2025 in the open source world. And so I'll talk through this really special kernel. So to get started, I'm just going to talk through the prefill case. And the prefill case looks very similar to a standard group gem operation. It's going to sound very similar to you. So after the attention layer, we'll have X, and we'll have top K IDX, and then we'll have the number of tokens that you're going to send to every rank. And the dispatch kernel takes in all of these as input. And the output of the dispatch operation is a recvx, which is the number of received tokens and the number of hidden tokens, as well as the indices of those received tokens. So after this dispatch operation, basically every rank has a buffer that gets allocated dynamically. So you can see that if 10 tokens got routed or 100 tokens got routed to that particular expert, you'd have a different size buffer. And this buffer gets allocated dynamically. And so the dispatch operation basically handles sending into this dynamically allocated buffer. After the dispatch operation, we'll do what's called a permute operation, which takes the received X, and it takes the top K IDX for each one of those received X's and rearranges them such that the tokens for expert 0 are in the first row, the tokens for expert 1 are in the second row, so on and so forth. After the permute operation, we do the gem, we do the activation function, we do the other part of the gem, so the W2, and then the unpermute puts it back. And so the prefill case looks very, very similar to kind of a standard group gem. This is a very, very common way, and the DPP high throughput kernel basically deals with just sending the token to the proper rank. I really wanted to show the DPP high throughput case to contrast it with the decode case. And in particular, the decode case for DPP low latency is specifically optimized to work with CUDA graphs. And so CUDA graphs have a very important property, which is that we can't sync between the GPU and CPU, and all of the buffers need to be allocated statically upfront. And so for DPP low latency, if you remember, one of the key things in the high throughput case is that the buffer gets allocated dynamically. So every rank gets a different number of tokens depending on where the router chose to send it. And so with DPP low latency, rather than having these dynamically allocated buffers, we have fixed static buffers that get created with some sort of max size. And the DPP low latency kernel is responsible for not only sending the tokens into this pre-allocated buffer, but also providing this recv count, which basically says how many of the tokens are invalid versus valid. Then, as you can see, the DPP, the Deep Gem kernels have a batched variant where rather than doing this permute and then standard group gem operation, the batched variant takes directly in these recv(x) tokens and then the recv counts and skips doing the computation on the basically garbage tokens. And only does the computation on the tokens that are really valid inside of that pre-allocated static buffer. And so this is extremely efficient because there's no permute operation. And very, very importantly, this is compatible with CUDA graphs, since the buffer is statically allocated and there's no CPU-GPU sync that occurs. So this is a very, very subtle difference between the prefill case, which looks like a very standard group gem operation, versus the decode case, which is doing all this really special magic to make this dispatch gem operation compatible with CUDA graphs and very, very efficient in a low latency case. I know I got a little bit into the details there, but I think that a lot of, when DBP and DeepGem first came out earlier this year, I don't think I really appreciated like how special this kind of decode case is to make things compatible with CUDA graphs. All right, so even with those optimizations, I just wanted to share what a chart looked like of the time in an individual layer of DeepSeek with these optimizations. So this is a slice from where we were, I would say, maybe like 3 or 4 months ago, which shows a kind of single layer of DeepSeek. So we have the QKV, we have the attention operation, we have the OPROJ, we have the router, and this big center item here is that dispatch MoE combine operation. So this, I think, is running expert parallel 32. So this is 4 nodes running over InfiniBand. And the key thing that jumps out is even with this amazing DeepGem, DPP stuff that I just talked about, this is a decode step. I think there's 256 requests. It's a decode scenario. We can still see this dispatch combine operation. These DPP in the light blue are taking up almost half of the time of the layer. So a really important optimization that we did to squeeze out that last bit of performance and deal with this, how much time was being spent in DeepGem, was to do something called dual batch overlap. And this was one of the things that DeepSeek released in their open source week, which basically tries to use micro-batching to overlap the collective communications with the gem operation. So one of the key things in this layer here is the deep EP kernels are using the InfiniBands. It's using that high performance networking. So while the DPP kernel is operating, the actual tensor cores are sitting idle. So one very common strategy when you have multiple different resources in a GPU is to try to split the work into different steps and do the operations in parallel. So a very common technique for this is to do something called micro-batching. And what micro-batching is let's say we have 100 requests in an individual DP rank. We're going to split that into 2 smaller requests of size 50 and do those operations at the same time. And what we will try to make happen is to have the DPP low latency operations for microbatch 0 running at the same time as the gem operations for microbatch 1 to effectively overlap the send receive with the actual kind of gem operations. A very standard way to try to do this type of microbatching in most things where we've done this in vLLM is with having multiple CUDA streams, where you actually launch 2 separate CUDA streams, run one microbatch in CUDA stream 0, one microbatch in CUDA stream 1, and hope that you get overlap. And this is actually what we do for the DPP high throughput prefill case. But because DPP low latency is an RDMA kernel, we actually can have a little bit more fine-grained control over how we do the microbatching and can actually do this in a single stream, basically by splitting the dispatch combine operations into 2 steps, which is the send and the receive. So the key idea is after we run attention for microbatch 0, we're going to do the send operation, the dispatch send operation for microbatch 0, and immediately start doing attention for microbatch 1. Attention for microbatch 1 can be happening while the RDMA for the dispatch send is going on in the background. Then we do the receive for microbatch 0 and do the dispatch send for microbatch 1 while the MoE is going on for microbatch 0. The RDMA is happening in the background for microbatch 1, so on and so forth. And this allows us to have really, really fine-grained control and effectively perfectly overlap the the dispatch combine operations with the MoE layer. And so here is what this actually looks like in what is basically today's implementation of dual batch overlap in vLLM. So this is an example of a single layer. One of the things you're going to notice is every operation is now there twice because we have split things into a microbatch. So what you can see is we have this forward flash, this void flash forward. This is attention for microbatch 0. You can see there's a really, really small previous ubatch 1 combine receive and current ubatch 0 dispatch send. So you can see we're sending the dispatch operation. It's returning immediately because we're not blocking on it anymore. After we do the dispatch send for current batch 0, you can see that we're immediately going into attention for microbatch 1. After attention for microbatch 1 is done, we call dispatch receive for microbatch 0 and immediately do the dispatch send for microbatch 1. Then we have the MoE going on for microbatch 0. We call microbatch 1 dispatch receive. We call microbatch 0 combine send. We do the MoE for microbatch 1. And then we do the combine receive for microbatch 0. And so you can see that there's, in comparison to what the chart looked like a long time ago, where the DPP kernels were taking almost half of the time of an individual layer, we can see that we're only really spending time from the point of view of the GPU in this combine receive for microbatch 0, which is much, 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 much smaller in the total end-to-end runtime. And this is over 9 nodes. So this is running with EP72, which is actually quite a large deployment, 256 concurrent requests per rank, 2K ISLs, 2K OSL. So a real deployment at very, very large scale. And we've effectively been able to hide almost all of the collective communication operations. And so today, what this means is with all of these optimizations, and there's a few other ones I didn't talk about here, such as EPLB, we're able to achieve 2,000 tokens per second per GPU on H100 for this kind of decode case with 2,000 ISL, 2,000 OSL. And what we can see is that this scales really, really well. So with 32 GPUs, so this is 4 nodes, we're able to get around 2.2K. With 72 GPUs, this is right around 2,100. With 96 GPUs, this is right around 2,000. And obviously, as we go up to 96 GPUs, we have much, 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 much more KV cache available. So you could run much longer requests. You could increase your batch size more and actually get more throughput. This looks at a fixed 256 concurrent requests per EP rank. But all of this is working really, really well. And it was a lot of engineering effort to get all of these optimizations to work together. So that's the efficient gem in dispatch combine. But what is PD? So why do we need to do PD disaggregation? So with PD disaggregation, the key idea is that we're going to have 2 nodes of vLLM, one that's specialized for prefill work and one that's specialized for decode work. This is really needed for 2 reasons. One is I just talked about the decode case and the prefill case for deep gem and DPP. And so a very obvious thing is it would be great if we could have a prefill worker that was always doing work with DPP high throughput and a decode worker that was always doing work with DPP low latency. But more importantly, we really want to load balance and have uniformity across the DP ranks, which is to say that if you have 96 ranks, if any of those requests is doing prefill work, now every single rank is going to be bottlenecked by the prefill work because we're doing the forward pass altogether. And in addition, it's actually worse than this because not only is it going to be bottlenecked, but you're going to have to fall back to the DPP high throughput case since all the ranks have to be doing the same kind of dispatch combine operations. So the PD disaggregation is very, very useful for enabling us to specialize the P and D workers and then also to ensure uniformity of all of the ranks when they're operating together. So we really need 2 things to make this happen. One is an orchestration framework and protocol to be able to coordinate the requests. And then the second is efficient KV transfer. So at Red Hat, we launched a project in collaboration with Google and others from the vLLM community to build an orchestration framework for serving LLMs. It's called LLMD. And one of the features that we have in LLMD is the ability to do PD disaggregation serving requests. So in our architecture, requests will come into a gateway. The gateway will call out to an endpoint picker, which will schedule the request. And the endpoint picker is really responsible for choosing which prefill worker and which decode worker to do the request. Now, this is one architecture. You could have really any kind of router here to do this top part. But the endpoint picker will then send the request to a sidecar. This sidecar forwards the request onto a prefill worker. So this worker 3 here is a prefill worker. The prefill worker will process the prompt, and it will then stop after processing the prompt and return some KV transfer metadata. This KV transfer metadata includes information about which KV blocks have the token IDs associated with this prompt. We send it back to the sidecar. Sidecar sends the request to the decode instance. The decode instance sees this KV transfer metadata, executes an RDMA transaction using a library called Nixel, which we've collaborated really closely with the NVIDIA team to bring into vLLM, which will actually pull the KVs from the remote instance, and then the decode worker can continue processing from there. So we need some sort of orchestration to effectively do this transaction, and we've developed a protocol using this KV transfer metadata to be able to coordinate these transactions. And so Nixel is a really, really nice library, which allows us to do things like say, hey, I want to do an RDMA of a block in my local branch. Maybe my block ID is 4 and 6, and I want to do an RDMA which pulls from remote block 05 into that block 06. And so Nixel has APIs that allow us to make it a lot easier to work with RDMA, to register these blocks, and to be able to effectively do really simple APIs for executing these RDMA transactions of the form described here. But what's really nice about Nixel is it kind of abstracts away a lot of the underlying implementation. So by default, we use UCX, which is a transfer library that allows us to execute remote transfer operations through InfiniBand or Rocky or even TCP. But Nixel also supports other backends such as Mooncake transfer engine. So it provides a lot of flexibility that allows us to support a wide variety of different transport protocols. Additionally, especially with InfiniBand and Rocky, Nixel and UCX support zero-copy GPU direct, which allows us to really do these transfers with very little memory overhead. And so inside of vLLM, we've made all of this KV transfer happen asynchronously. So inside of the D worker, basically every step we have in the scheduler, if we have a KV transfer request, we call request need load, which will say, hey, this request has remote KV transfers. In the worker, we'll have the Nixel connector sitting in the worker. The worker will call read blocks, and this Nixel connector will start a KV transfer operation. So we call this xfer operation, which initiates a transfer. We don't block on this transfer, so the Nixel connector will return immediately. The scheduler is able to continue on doing work on other requests, but every single step, we look for this get notif item inside of Nixel, which tells us, hey, this transaction is done. Once we get this get notif operation, we say, OK, this is finished. The finished receiving goes back to the scheduler, and then the scheduler can treat the request just like it would for any other request. And so this allows us to really integrate Nixel very nicely into vLLM, which makes all of the KV transfer operations happen asynchronously relative to the engine execution. It's also RDMA-based, and so it doesn't contend with SM resources that are being used to kind of process the model. And so in addition to all of the items that I talked about for YDP, we also find that PD disaggregation can be very useful for serving even smaller models in a single node environment. So here's an example of a chart. This is GPT OSS on, I think this was running on 16 H200s, so 2 nodes. And I have a Pareto chart here. The x-axis shows tokens per second per user, so this is the latency. The y-axis shows tokens per second per GPU, which is the throughput. And the overall goal is that we want to be up and to the right. So for a given latency, you want to have more throughput, or for a given latency, for a given throughput, you want to have more latency. And what we can see is that in medium serving regimes, so in super low latency and super high throughput regimes for the single node, the aggregated and disaggregated cases get pretty close. But for the kind of medium concurrency ranges, we can see that the disaggregated serving offers a nice speed up. So it's a technique that can be used not just for these YDP deployments that I talked about, where it's actually super critical because of all the reasons I talked about of uniformity across the ranks, but also for more standard serving options. So anyways, thank you all very much for listening. I know this was a very technical talk, so happy to take any questions after the fact. Thank you very much.
Yeah, so actually we know that NVIDIA also have Dynamo kind of doing that. So I just want to know what's the maturity of this feature, like disk aggregated serving, and is it like a beta, or can we already use it? And also besides VM, you mentioned actually we need to have routing and also the every that service, right? So in order to set up those things, what shall we do? What project we should go?
Yeah, sure. So in terms of PD disaggregation, this has been inside of vLLM for, I'd say, like the last 6 months or so. Was sort of the first implementation was sometime back in April. So since then, things have gotten hardened quite a bit. And we've actually seen some of our large-scale users start to put PD disag into their production environments. And so, yeah, like I definitely think the feature is good to go and like ready for like prime time deployments. So I'm also very happy to provide support to anyone that wants to get up and running with this feature. It's very near and dear to my heart. In terms of the YDP, this stuff has been being worked on for a long time. I'd say within the last 2 or 3 months is when we've started to be able to hit this 2,000 token per second per GPU setup. And we've especially really see a lot of usage for YDP in like RL environments. Like I kind of mentioned, a lot of the benefit of YDP is the increase in the KV cache size. Like that's really why it YDP really drives the most benefit when you have these, really want to crank the batch size as high as possible by having as much KV cache memory as you might want. And so things like synthetic data generation, RL workloads, where you're trying to churn as many tokens as you possibly can out of the GPU, that's where we see a lot of interest in the YDP feature, and we've been collaborating with a few labs to help them get up and running with, vLLM's YDP support inside of their RL rollout frameworks. In terms of the orchestration layer, LLMD is the project that I personally work on. That's very centered on Kubernetes. So it's very targeted at folks that want to deploy production services. So more of the PD stuff. We'd love to have anyone who wants to contribute or try it out. We also, of course, have NVIDIA Dynamo, which is another framework that offers a similar set of features to LLMD, which is a little bit less tied into the Kubernetes ecosystem. And I'm sure there's other projects out there as well. Like I've seen some people write their own router. The protocol is not all that complicated, so people can figure it out. I think the space is very immature in terms of not immature, but the space is there's a few projects that are kind of up in the center of the orchestration layer. There's lots of other features such as like KV-aware routing, or KV cache offloading to disk, or smart load balancing. How do you roll out new versions of the service? So I wouldn't make the decision solely about the PD disaggregation feature. And so one of the things we've tried to do in LLMD is make all these different pieces composed together. But yeah, we'd love for anyone who wants to try any of these features out, please feel free to reach out and I can help you get it up and running. Yeah.
Cool, and last question.
How are you guys thinking about like elastic EP in LLMD?
Elastic EP is a very challenging piece. so one of the key negatives of YDP as well as of PD disaggregation is it increases the blast radius of failures. For instance, if you're running on 96 GPUs, if any rank has a fault, that has a really good chance to take down the entire system, right? And so implicitly, as you kind of couple different nodes together, the system becomes less tolerant to faults. So right now, in LMD, right now, the key kind of place where we need to make improvements to enable elastic and fault-tolerant YDP is inside of the vLLM level, and also not even in the vLLM level, but also in the collective operation level. So for instance, you can see why you would have ranks hang. Let's say you have 96 ranks that are talking, ranks 1 through 52 and 52 through 96 are executing a forward pass. They all issue a dispatch operation, and if rank 52 is dead, it's not going to respond to that dispatch operation, which is going to cause all the other ranks to fail, right? And so the current place where we're collaborating with the team at NVIDIA and others in the community and also the folks at Anyscale is to try to get this low-level collective stuff. There needs to be new APIs and new lower-level things to be able to recover from those types of issues before the higher-level frameworks are able to actually take advantage of those APIs. So that's kind of how I really see the problem. It's a huge problem in the ecosystem, but a lot of the lower-level stuff needs to get sorted out to make things robust. And I know the Nixel team has been working on a lot of this so far, and so we're really excited to try to pull some of these things in and then make the higher level frameworks be able to use those lower level things to make a more robust system over time. But to answer your question, in LLMD right now, the philosophy that we're taking is when we do have errors occur, to detect them as soon as possible, recycle the pods as fast as possible, get the startup times to be as fast as possible, until these lower level things start to get a little bit more mature for production usage. And then we'll switch over to try to be a bit more resilient to failures. Yeah.
All right, one last round of applause for Rob, please.
Thanks, everybody.